Now recall from single variable calculus that if you want to determine the area underneath a function between two values, the idea is to approximate the area using rectangles. So what you need to begin with is what's called a partition. Now in the partition, you take the interval a to b and you subdivide it into n equally spaced subintervals. Now this requires a set of points. So this first location is x0. Come up with a second location x1 and then x2. Each of these is separated by the same width. Now you pick some sample point somewhere in that subinterval and you build a rectangle based on where that sample point intersects your function. So if you do this for all the subintervals, the area underneath the curve gets approximated by the areas of these individual rectangles. The height of the first rectangle is f of x1 star times delta x. Now here is this x1 star. It's called the sample point on that first interval. Then you've got the second rectangle, height times width, and there's the x2 star. So on and so forth until you get to the very final one of these rectangles. Now this can be written in sigma notation or summation notation, and here we've got some xi star times delta x. Now this type of expression here is called a Riemann sum. If we want to define the area, what we'll do is take more and more of these rectangles and make them thinner and thinner and thinner. And if we continue to refine the rectangles in this way and we come up with an answer, if we come up with a number, that number is what we define as the area. So this is the definition if this limit exists. Now remember that here we are interested in the function being a positive function on our subinterval. So what this did is it led mathematicians to define the definite integral. So the definite integral is defined according to this calculation involving the limit of a Riemann sum. In the special case that your function is positive, the result of the definite integral will represent area, but generally the definite integral doesn't necessarily connect to area. When does the definite integral exist? When is f integrable? This is the phrase that we use. So there are several sufficient conditions that we can talk about. Sufficient means these conditions will do the job of making sure that the function is integrable. So if the function f is continuous on a, b, this limit will exist and the function will have an integral. Now the other condition here is if your function is piecewise continuous on your interval a, b. Piecewise continuous is something a little weaker or a little less well-behaved than continuity. Piecewise continuity means that your function is bounded on the interval ab, which means that the size of your function less than or equal to some positive number, and f has a finite number of points of discontinuity. So that means breaks or holes or gaps, etc. So for example, functions that do something like this can be integrable on your particular interval. Knowing whether a function is integrable just means that you know that this definite integral will exist. But a more important question is, how do we actually calculate this definite integral? Other than very, very simple cases, it's almost impossible to use Riemann sums. We're saved by the fundamental theorem of calculus. Now, the fundamental theorem of calculus says if your function f is continuous on this interval ab, then the value of this definite integral can be very simply computed by taking the difference in the antiderivative of the function. So the antiderivative is a new function that's related to your original function in this way. If the value of your function is greater than 0, then the definite integral calculates the area, and otherwise, this is going to produce what's called the net area, or sometimes it's called the signed area, which just means add up all the areas that are above and below, and you could end up with a positive or negative number.